Okay, so we can start our seminar now, and the talk will be about the alpha induction tensor categories and operator algebras. Liz.
Okay, thank you. So I thank the organizers for the invitation to speak. I'm very glad to give a talk on this online seminar. So my title is Alpha Induction, Tensor Categories and Operator Algebras. And probably you don't know what the alpha induction is. This is a certain induction procedure, and I'll certainly explain this in this talk. So in the operator algebraic approach to mathematical physics, so the Jones theory of subfactors, which produced the Jones polynomial for Northern rings, it has played an important role. And from a contemporary viewpoint, a key tool in this study is the tensor category, possibly with the braiding. And in today's talk, I will explain alpha induction, which is a functorial method to produce a new fusion category, some kind of finite tensor category, from a sister braided fusion category and a Frobenius algebra in it. So it has close connections to two-dimensional conformal field theory and condensed matter physics. So I'll explain certainly these relations in my talk today. So the outline of my talk is as follows. So first, I'll explain some general thing about braided fusion category and operator algebras, and then I'll explain the alpha induction and the mathematical physics. And then the last part is the newest part. We have a certain combinatorial notion, which is called biunitary connections, and I'll explain the alpha induction in the framework of this biunitary connection. So I first start with something very elementary about the fusion categories. So I start something which is extremely elementary. So everyone knows that a finite group is given as follows. So a finite group G consists of the following ingredients. So we have an associative multiplication. Of course, we have some binary operation. Then we have the identity element. And also each element has the inverse element. So these are axioms for a group. And particularly today, I basically mean a finite group. Then for a finite group G, we consider the set of its all the finite dimensional unitary representations. Yeah. But there is the question. I see Kirillov raised the hand. Is there a question? No? Okay. So we now consider the set of all the finite dimensional unitary representations of a fixed finite group G. Then we have the following structures. So if we have a general finite dimensional unitary representation, then it has an irreducible decomposition into finitely many pieces. So this is different from a case of the finite group structure. But then the rest is somehow similar to the group structure. So for group representations, we have a tensor product operation, so which is a kind of product operation, and also it is also associative. And also, just like the identity element in the group, we have the identity representation, which is the one-dimensional representation where all the group elements are mapped to just one, the number one. Also, for each group representation, we have the dual representation, or sometimes called a contra-gradient representation. This is a kind of inverse representation. So in the sense, in the following sense. So for a group element G, we have another element H such that GH is equal to hg is equal to 1. This is the inverse element, of course. And in the group representation case, suppose we have an irreducible representation pi. So we want to find something, some sigma such that pi tensor sigma is equal to the identity representation, but of course this is not possible in general. It's almost always impossible because the dimension of pi is not 1. But still we can impose the condition that pi tensor sigma contains the identity. Such sigma is a kind of inverse representation, which is called the dual representation of pi. So we have something like the inverse element in this situation. Then, so we have a tensor product operation, we have the identity, and we have a kind of inverse operation. And then we can make an abstract axiomatization of this structure, and it gives a fusion category. So we have only finitely many irreducible objects, and we have a notion of intertwiners between group representation, so that gives a notion of morphism. So we have an object and morphism, and we can compose morphisms and usual axioms for category. So this gives a notion of a tensor category, because we have a tensor product operation on the objects. And in this situation, we have only finitely many irreducible objects, and this kind of thing is called a fusion category, because this tensor product operation is often called a fusion product in this context. Then, so this is an abstract notion of a fusion category. Then I'll explain its connection to operator algebras. So let M be a certain operator algebra. Actually, this is something called a type 3 factor, but it doesn't matter. So this is some kind of infinite dimensional algebra. Then we can consider an endomorphism. Actually, in a typical setting, this is automatically an injective. So, and also we are interested in the case where it's not an automorphism. So from a M into M, so the image is strictly contained in M, which is isomorphic to M. So we are interested in this kind of endomorphism. So we consider the endomorphism lambda, then we look at the range of this endomorphism. Then we can consider the notion of the Jones index. So this measures the size of the range relative to the original algebra M. So both are infinite dimensional, but somehow still we can measure the relative size of the image with respect to the original algebra. Then this is a kind of dimension, but it is called the Jones index. And then this kind of endomorphism gives an object of a tensor category. Then the tensor product operation is given by a composition. So if we have two endomorphisms of the same algebra, of course, we can compose them. And this composition really gives the tensor product operation. Then we need the kind of dual endomorphism in situation, a dual object. And then in this situation, we have something called a conjugate endomorphism, lambda bar. And this is given in terms of the modular conjugation operator arising from the Tomita-Takesaki theory, but the details don't matter. So we can somehow define the dual endomorphism lambda bar. And this is really behaves like the inverse element. Then if we have finitely many irreducible endomorphisms, so we have a notion of a direct sum and irreducible decomposition of endomorphisms. Then we have if we have a closed system of finitely many irreducible endomorphisms, then we can make a fusion category. So this is one realization of a fusion category within the framework of operator algebra. Another related but different construction of a fusion category in the framework of operator algebra is the following. Let M be another type of operator algebra. Then an MM bimodule of H, an MM bimodule H, which is a Hilbert space with the left action of this operator algebra and the right action of this operator algebra. Then we again have a notion of the Jones index for this Hilbert space H as an MM bimodule. Then we still have the notion of the finite Jones index, and this is a kind of finite dimensionality. Then this kind of bimodule gives an object of a tensor category. Then the tensor product operation is given by a relative tensor product of two Hilbert spaces over M, the same Hilbert, the same operator algebra. So we have a bimodule, then we have a relative tensor product structure, and in this way we can define tensor product in the tensor category. And then in this situation, the dual bimodule is easier to define. Just we look at the dual Hilbert space, the conjugate space. Then it has a natural action of the M and M. So we have an H bar in this setting, and this is really a dual object in this situation. And also, yeah, in this situation, it's easy to define a direct sum and irreducible decomposition. So in either way, we can construct a fusion category within the operator algebraic setting. Then next, I talk about a braiding. So yeah, in a general setting, we start with an example of group representation. If we have two unitary representations, pi and sigma, of the same group, then the tensor product pi tensor sigma and sigma tensor pi are trivially unitarily equivalent, of course, it's easy. But then this kind of unitary equivalence for two tensor products is not assumed as an axiom of a fusion category. So in general, the pi tensor sigma and sigma tensor pi could be entirely different in our setting, and this is the case in our operator algebraic setting. But then we have an important subclass of fusion categories for which this kind of commutativity of tensor products holds in some mathematically nice way. And this kind of commutativity of tensor product is called braiding, because this is similar to switching two wires. So we have two wires, and we have overcrossing and undercrossing, and this is in correspondence to two ways of switching tensor components, so pi tensor sigma and sigma tensor pi. So this kind of braiding comes in the pair, overcrossing and undercrossing. And then in the groups representation situation, so in the case of pi tensor sigma and sigma tensor pi for two group representations, we can consider overcrossing and undercrossing, but they are actually the same. So in this sense, in this setting, it doesn't make much sense to distinguish two ways of crossing. But if these two, overcrossing and undercrossing, if they are really different, it's more mathematically interesting. And in this situation, the fusion category is called a modular tensor category, where this is not a real mathematical definition, but we can make a real definition based on this. So modular tensor category, this is something important in many applications of tensor category theory. Then, I next explain why and how this kind of thing is related to conformal field theory. So in the setting of two-dimensional conformal field theory, this is a quantum field theory, a kind of quantum field theory on the two-dimensional, 1+1 dimensional Minkowski space with conformal symmetry. Then in the standard procedure, it splits into two chiral halves. And then two chiral theories live on the one-dimensional line, just R1. But then we can make a compactification of this real line to get the one-dimensional circle. And then we get the conformal field theory living on the circle S1. Then so we get a quantum field theory on the one-dimensional circle S1. And then in the operator algebraic approach to quantum field theory, we consider a conformal net A of I, where I is an interval contained in the circle. So here, each A of I is a von Neumann algebra, so some kind of operator algebra generated by observables in I. So this in general, for a fixed space-time region, we consider all the observables contained in this space-time region. Then these observables are represented by self-adjoint operators on the Hilbert space of the states, just like the standard quantum mechanics. Then for a fixed space-time region, we have lots of observables, so we have lots of self-adjoint operators. Then they generate a single operator algebra. And in this setting, which is written as A of I. So in this way, we get a family of operator algebras parameterized by space-time regions, which are intervalled in this extension. Then in this standard setting, this A of I is automatically a specific von Neumann algebra called Arakiewicz type 3-1 factor. Well, it doesn't matter, but I just mean that so each operator algebra is automatically uniquely determined. So each operator algebra doesn't contain any information about the quantum field theory. But as a family, there are relative relations among these operator algebras. Then they describe the conformal field theory. Then finite dimensional unitary representation. I mean, this is a finite in the quantum sense, not the ordinary sense. So in the quantum sense, we have quantum dimensions and we have notion of finite dimensionality. So in this sense, we have finite dimensional unitary representation of this conformal net. So this gives a braided category. So we automatically get a braiding in this extension. This is called Doplicher-Haag-Roberts theory. This is an old theory in like 50 years old. And then they have a notion of super selection sectors. So we have a braiding structure among super selection sectors. Then if we have only finitely many irreducible representations or only finitely many super selection sectors, then we get a modular tensor category. This was proved by Longo, Mug, and me many years ago. So in this way, we get a modular tensor category from a conformal field theory in the operator algebraic setting. Now, another formulation of a conformal field theory is the vertex operator algebra, which is also well studied and well known. This is based on a Fourier expansion of operator variant distributions on the circle. So the circle is a kind of space-time. Well, it has only dimension 1, but still it is a kind of space-time. Then a quantum field is an operator variant distribution on the space-time. So we have a quantum field on the circle. But then this is one-dimensional circle, so we can make a Fourier series expansion. Then we get a vertex operator. And then we have certain algebraic system consisting of vertex operators. And this is called a vertex operator algebra. Then the most famous example is, of course, the moonshine module, moonshine vertex operator algebra, which arises from the moonshine conjecture, which connects to the monster group and the elliptic modular J function. And this is also related to the Leech lattice in dimension 24, realizing the densest sphere packing. So under some natural finiteness assumptions, the representation category of a vertex operator algebra is also a modular tensor category. So this setting is very similar to something in operator algebra. Then, so these two different mathematical axiomatization of a chiral conformal field theory have been separately studied for many years, say 30 years or so, more than 30 years. Then recently, in the last, say, 5-6 years, direct relations between two approaches, conformal net and vertex operator algebras, have been extensively studied by many people, including myself. So we have a lot of recent progress in this direction. Then, so we have certain graphical calculus handling braided fusion category. So suppose we have a braided fusion category, then an irreducible object in the category is represented with some kind of wire, like this picture. So in the picture, the left picture has 3 wires, and they are labeled as lambda, mu, nu. Then also, so when on the right picture, we have 2 wires, lambda and mu, and they go down. So lambda and mu merge into a new wire, nu. Then we have a triple point here labeled with T. And so this is an isometric intertwiner T, which is a homomorphism from lambda tensor mu to nu. with an approximate normalization. And also, this normalization is given by the following formulas for d lambda, d mu, and so on. And this d is a kind of quantum dimension of representation. So, but this fourth root normalization is just a standard one, so it doesn't matter so much. So up to these normalizations, these two pictures represent isometric or co-isometric intertwiners. So the left one is from nu to lambda times mu. The right one is from lambda times mu to nu. And note that in this setting, we read our diagram from the top to the bottom. For the left picture, this is an intertwiner from nu to lambda mu, so from the top to the bottom. But some authors use the opposite convention. They read the diagram from the bottom to the top, but I use this convention in this talk, where it doesn't matter so much. Then a Frobenius algebra in the braided fusion category. So I explained this one in the framework of operator algebra. So suppose we have a subfactor n in M. So this is a infinite dimensional operator algebra n, which is somehow called a factor, which is contained in a larger operator algebra M. So in the operator algebraic terminology, this is a one factor contained in another factor with finite Jones index. This is called a subfactor. This is the standard setting of the Jones theory. Then we also impose some kind of finiteness condition, which is called the finite depth. This is something like rationality in the conformal field theory or quantum group setting. In this setting, they usually call rational in this setting, but in the operator algebra, this kind of finiteness is called the finite depth condition. So, Then here, so we regard M as an n bimodule. Then we can make an irreducible decomposition of this one as n bimodule. Then this finite depth condition means that we get only finitely many n bimodules arising from this tensor power construction. Then these n bimodules give a fusion category. So we have only finitely many irreducible n bimodules, and this system is closed under the tensor product and dual operation. And then in this tensor category, we have the original bimodule, M itself, as an n bimodule. And this gives something called an algebra in a fusion category. And then this kind of algebra in our setting is called a Frobenius algebra. This is a notion in the abstract tensor category. And then if the original fusion category is braided, furthermore, braided, then we have a notion of commutative and non-commutative Frobenius algebra. Then a commutative Frobenius algebra is more important. For modular tensor category arising from a chiral conformal field theory, a commutative Frobenius algebra gives an extension of a conformal field theory. So this gives larger conformal field theory, which extends the given conformal field theory. Then in this setting, we can explain alpha induction for endomorphism. So in the classical setting of group representation theory, if we have a representation of a larger group, we can, of course, restrict it to a smaller group. That's trivial operation. But conversely, if we have a representation of the smaller group, we can make a unitary representation of the larger group. And this is an induced representation. So we want to have something similar here. So we have a smaller conformal field theory and a larger conformal field theory. And suppose that we have a representation of a smaller conformal field theory. Then we can make an induced representation of a larger conformal field theory. And then this construction can be done within the setting of the abstract fusion category and also in the setting of operator algebra. And now I explain this construction in the setting of operator algebra. And then in the setting of operator algebra, this construction is called alpha induction. So this is just some special version of the induction procedure. And then, as I said, in this setting, in one setting, one object of a fusion category, so which is something like a representation, this is given an endomorphism of an endomorphism of an operator algebra. So in this framework, our induction procedure gives an extension of an endomorphism from a smaller algebra to a larger algebra. So this is our construction. So in an entirely abstract setting, if we have a smaller algebra and large algebra, and if we have an endomorphism of a smaller algebra, and we want to extend the endomorphism to a large algebra, then in general, this is not possible at all, of course. But then under this setting, based on braiding, we can prove that this extension is possible. And so this extension procedure is given by this formula. So suppose we have a lambda, which is an endomorphism of the small algebra, and this is an object in the fusion category. Then we want to make an extension of this endomorphism, and we write alpha lambda for this extension. But then this depends on the choice of a braiding. This is related to braiding, and this is why we need a braiding structure. Then for braiding, we always have a positive braiding and negative braiding. I mean, overcrossing and undercrossing. So we have two choices of a braiding. And depending on the choice of this braiding, we have two extensions. So alpha plus lambda and alpha minus lambda. And both of them are expressed in a single formula here. And here, so this iota is the inclusion map into M. Then we have certain bar, iota bar here, and also we have an inverse map here, but where the details don't matter. And also this epsilon plus minus, this is a braiding operator. And this theta is some kind of the original Frobenius algebra object, an algebra in the tensor category. And this lambda is the original endomorphism. And here we have a braiding, and this is a unitary operator, so we can make an adjoint operation. And this lambda is the original endomorphism. Then iota bar is the dual operation, dual object of the inclusion map. Then, but in details don't matter, but it's important that we can write down everything explicitly, so we can make explicit computations of this alpha induction. More specifically, this alpha lambda is the same as original endomorphism lambda for X in the small algebra. So this is really an extension. And then this large algebra is generated by the small algebra under a single element, isometry V. So in order to extend this endomorphism, it's enough to specify the image of this new element V. Then it's explicitly written in this way. So this is a braiding operator. So yeah, the image of this braiding, this isometry is given by braiding unitary and this original isometry V. So this construction was first defined by Long and Leland more than 20, maybe 25 years ago, and studied by, but they basically only gave a definition. More detailed studies were given by Fenshu, Beckenhauer Evans, and also Beckenhauer Evans and myself. So after our work, we have a detailed understanding of this induction procedure. Then, so the meaning of the alpha induction in conformal field theory is the following. So one conformal field theory is described by a conformal net, a family of operator algebra. Then suppose it has only finitely many irreducible representations. So this is a rational conformal field theory. Then in this setting, its representation category is a modular tensor category. Then, as I said, each commutative Frobenius algebra in this setting corresponds bijectively to a conformal extension of this original conformal net. So if we have a larger conformal net containing the original conformal net, then we get commutative Frobenius algebra in this representation category. And also conversely, if we have a commutative Frobenius algebra in this representation category, we can make an extension of a conformal net. We can produce a larger conformal net. Then, so fix one extension B of I of A of I. Then the irreducible object that simultaneously arise from positive induction and negative induction exactly corresponds to irreducible representations of the B of I. So in the classical setting, induced representations really arise from this induction procedure, but here we have more subtle situation. If we have only positive induction, then we don't get an irreducible representation of the larger family. And if we apply only negative induction, we still get an representation category of the larger conformal field theory. And if you look at the intersection of positively induced representation and negatively induced representation, then we exactly get a real representation, genuine representation of the larger conformal field theory. So here we have more subtle situation. And also the Frobenius algebra is recovered from the so-called modular invariant matrix here. Then here I start with something which looks entirely different. So this is really an operator algebraic study of this kind of setting. Yeah, this kind of structure also naturally appear in the setting of studies of quantum groups in the operator algebraic framework. So consider 4 finite dimensional operator algebra. They are really finite dimensional thing. So finite dimensional fifth algebra is really just a direct sum of n by n matrix algebra, so something really linear algebra. Then so we have 4 finite dimensional operator algebras, A, B, C, D, and suppose we have a trace, which is a linear functional on D, which satisfies the trace of x times y is equal to trace of y times x, just like the ordinary linear algebra trace. And then we say this is a commuting square if the restriction of the, so we have something called a conditional expectation from D to B and also C to A. So if we have a trace, this is really like a projection with respect to the L2 inner product arising from this trace. So we have a projection from D to B and from projection from C to A. And if we restrict this projection to the C, then if we get the projection from C to A, then we say that this is a commuting square. So this is a commutativity of a certain diagram. And also in a symmetric situation, we can also consider a projection from D to C and also B to A. And this is gives an equivalent condition. Then, in order to avoid some rather trivial examples, we require that some non-degeneracy of B and C. So we require that the product of BC spans the entire, the larger algebra D. This is called a non-degeneracy, but if you are not familiar with this kind of thing, this is not so important. But well, anyway, in this talk, I always talk about finite dimensional non-degenerate commuting square. So this is some kind of symmetric situation of 4 algebras. Then, so if we have an inclusion of finite, inclusion of 2 finite dimensional operator algebras, then we can represent this inclusion with a certain finite bipartite graph, which is called a Brattley diagram. So the vertex of Brattley diagram is given by a simple summand, so n by n matrix algebra, so simple summand of an operator algebra, and the edge of this Brattley diagram is given by a multiplicity of embedding. So if for a commuting square, we have 4 inclusions, so we have 4 Brattley diagrams. Then so we choose one edge each from 4 diagrams. Then from a choice of these 4 edges, somehow we can produce a complex number from such a square this is just a linear algebra where I omit details, but this is entirely elementary, something undergraduate mathematics. Then, so we draw this kind of picture. So we have a square picture, and for this left square, this x, y, z, w, they label for vertices of this square picture, and then edges of this square are labeled with Xi1, Xi2, Xi3, Xi4. These are 4 edges from the 4 Brattil diagram. Then this square picture represents a complex number. And also on the right, we also have another complex number, and this bar denotes the complex conjugate. So we have 2 complex numbers, one with complex conjugate, and we have summation of the product. Then here we have Xi1, Xi2, Xi1, Xi2, they are the same. But here Xi3, Xi3 prime, they are different. Xi4, Xi4 prime, they are different. Then we have a summation of Xi1, Xi2, so something common. So we have a summation of common edges. Then we should get the Kronecker delta, so 0 or 1, depending on whether this Xi3, Xi3 prime, Xi4, Xi4 prime, depending on whether they are equal or not, we get 1 or 0. So this is a kind of unitarity because these numbers give entries of certain large unitary matrix. So this unitarity is one axiom which is satisfied in the setting. And also, the biunitarity means these numbers are doubly unitary in the following sense. So this is one unitarity, and another unitarity is given by this formula. So we have one square picture. Then we make a reflection, a horizontal reflection of this graph. So here we have y, x, but on the right picture we have x, y. Here we have w, z, but on the right picture we have z, w. So we have horizontal reflection. So if we make a horizontal reflection, we should get the complex conjugate. So this by the again complex conjugate. So and then we get a new value w prime, which is basically a complex conjugate, but we also have some normalization arising from mu. So this is some kind of normalization given by Perron-Frobenius weight, or some kind of quantum dimension normalization. So up to this kind of normalization, we should get a complex conjugate for horizontal reflection. So this is a kind of another unitarity. So after this horizontal reflection, we should get, we also have unitarity for this W prime. This is another unitarity. So we have unitarity for W and another unitarity for W prime, and they together give biunitarity. And then in abstract setting, we have an assignment of a complex number to each square satisfying these 2 axioms. Such an assignment is called a biunitary connection. And this name connection comes from an analogy to differential geometry. So this connection is a kind of discrete analog of a usual connection in differential geometry. So we use this name connection. And this name is due to Ogniano. Then an example of such a connection on the Dinkin diagram. So we give an explicit example of a connection on the ADE Dinkin diagram. So we fix one of the ADE Dinkin diagrams, and we use it for all the 4 Brattil diagrams. Then let n be the Coxeter number of the Dinkin diagram, and then epsilon is the root of unity given by this formula. And we write mu x for the Perron-Frobenius eigenvector entry for a vertex x of the Dinkin diagram. Then our connection is given by the following diagram. So we have J, K, L, M. These are labels for the vertices of the Dinkin diagram. And we have no label for edges because each edge has no multiplicities. Then we have Kronecker delta of K and L, and we have this epsilon, this root of unity. And also we have Kronecker delta of J and M. We have epsilon bar for this epsilon. And also we have some Perron-Frobenius weight. And then this satisfies the unitarity and also the other unitarity. So this is an example of the Dinkin diagram. And actually, this is very similar to the Boltzmann weight in the lattice model situation. So here we have one graph, and we make a square from one graph, and we have an assignment of a complex number. This is really similar and essentially the same to the situation of the Boltzmann weight in the lattice model situation or IRF model situation. And exactly the same formula appeared in the setting, like Andrews, Baxter, Forrester model. So this situation is very similar to this lattice model situation. Then these connections actually give an object of a tensor category. So we have a tensor product of connections and a dual connection. So we have tensor product of the dual and the dual connection in the following. So if we have two connections, W1 and W2, and suppose the graph for C7 and this graph for C7, they are the same. This is assumed. Then we can compose two connections. This is just a vertical concatenation of the two connections. So W tilde is a new connection, and this is really like the usual concatenation of two, say, Boltzmann weight. So we have product of W1 and W2 over the common edge C7, and we have a summation over this common edge C7. So this is a product connection. And also for the dual connection, basically we take the complex conjugate. But now we have take a vertical reflection. So here we have V and W on the top, but here we have Z and W at the bottom. So we make a vertical reflection. So this C1 tilde is a reflection of the edge C1. So here we have an edge from C1 to C. So we have C1 from X to Z on the right picture, but on the left picture, we have C1 tilde from Z to X. So this is the horizontal, vertical reflection. So this vertical reflection basically gives the complex conjugate. This bar is the complex conjugate. So we have a complex conjugate, but again, we always have this kind of weight normalization, but this is not so important. So this bar, the dual connection is basically complex conjugate. So in this way, we can define the dual connection. Then this is also related to two-dimensional statistical physics. So in a general setting, we have a theory of tensor network. So we have a K-tensor is a finite family of complex numbers indexed by K indices. In our setting, this connection is determined by 4 edges. So this is a 4 tensor. So ordinary vector is a 1 tensor because it's given by 1 index. And also a matrix, an ordinary matrix. So matrix entries is given by AJK. So we have 2 indices. So this is a 2 tensor. And also the product of 2 matrices. This is given by a concatenation of two tensors. So we have AJK, BKL, then we have a product of AJK and BKL, and the summation of a common YK. So this is a concatenation of 2 tensors. So then similarly, we now have a 4 tensor. And then our 4 tensor is given in the following sense. So we have, in our setting, we have one biunitary connection. Then we have a horizontal reflection, double prime. Then we have make a concatenation, and then we have a new 4 tensor, and this is our 4 tensor, which we used. Which we use in statistical mechanics, two-dimensional condensed matter physics. So this is, and also we have some finite family of 4 tensors in this setting. So we have a label A here. And this arises from a label A from a biunitary connection. So such a 4 tensor has been used recently by physicists in studies of two-dimensional topological order. And this is a hot topic in the last, say, 5-6 years, and there are lots of really many papers. And they are interested in explicit computations using computers. And also, What they do is very similar to what we do in operator algebra in subfactor theory. So many of their formulas, their identities, their constructions can be translated into the operator algebraic setting, and also operator algebraic results give something useful in their setting. So this is really a new applications of operator algebra in two-dimensional statistical mechanics. Then, so in the remaining time, I'll talk about some new results, recent new results in this setting in connection to two-dimensional condensed matter physics. So we have a fusion category of endomorphisms and the connection. So suppose we have a fusion category of endomorphisms. So an object is given by an endomorphism of some infinite dimensional operator algebra. And suppose we have 6 objects, okay, irreducible objects, and they are labeled with lambda, mu, nu1, nu2, nu3, and nu4. They are irreducible objects, so irreducible endomorphisms of the same algebra, same operator algebra. Then we fix lambda and mu. This is why we use different labels, different symbols, lambda and mu. And then the other nu1, nu2, nu3, nu4 some possible different labels. Then we consider the following diagram. So in this diagram, so we have 6 edges, and they are labeled with lambda, mu, nu1, nu2, nu3, nu4. And we have 4 triple points in this picture. So we have 4 intertwiners. Right. So for this part, we have nu4 from nu4 to lambda times nu2. So the top triple point is an intertwiner from nu4 to lambda times nu2. And we have 4 intertwiners. So we compose these 4 intertwiners. Then this is an irreducible intertwiner, intertwiner from an irreducible object nu4 to an irreducible object nu4 itself. So this gives a scalar. So this picture is a composition of 4 intertwiners, which is a complex number. So this closed diagram gives a complex number. And so this is basically the same as the usual notion of 6J symbols in representation theory. And also in the quantum group theory, we have a notion of quantum 6J symbols. This is really the same idea. So if we have lambda and mu, and then nu1, nu2, nu3, nu4, then we get a family of complex numbers indexed by these 4 objects. Okay, lambda and mu are fixed. So we have the other 4 indices, nu1, nu2, nu3, nu4. So we have a family of complex numbers indexed by 4 objects. And this kind of thing, so this is really a 6J symbol. And this is also gives a bi-unitary connection. And in the subfactor theory, this kind of thing is a specific, this gives a especially nice class of bi-unitary connection. And in the subfactor theory, this is called a flat connection. So we have an example of flat connection arising from this way. So this is a particular standard construction of a flat connection from a fusion category. Then we want to formulate the alpha induction in this framework. So then we introduce the alpha-induced connection using alpha-induced endomorphisms as in the following picture. So here we have alpha plus lambda. So this on the upper left corner, our object is alpha plus lambda and A1 mu, and A1 and mu are some other endomorphisms. Yeah. Then on the upper left corner, we have alpha lambda plus A1 mu. And upper right corner, we have alpha plus lambda A2, and also some other endomorphisms at the 4 corners. And here now we have 2 more endomorphisms. So A1 lambda mu on the left, and A2 lambda on the right. And they are identified with the upper top corner, upper left corner and upper right corner with using braiding unitaries. So using the braiding unitary, actually we can also switch the order of alpha lambda plus A1 and also A1 lambda. A1 is some other morphisms. So so using braiding, we have now 6 endomorphisms, and we have some diagram involving 6 so 6 endomorphisms and 6 intertwiners. So this large diagram represents the composition of these 6 intertwiners. So at the right bottom corner, we have A4. So we compose these 6 intertwiners from A4 to A4. Then we get an intertwiner from A4 to A4. And because A4 is irreducible, this self-intertwiner is a complex number. So in this way, we get a complex number from this diagram. So in this way, we get a complex number, and it turns out that this gives the correct notion of alpha-induced connection. And then we can rewrite this diagram using a braiding operator. So recall that we have 6 objects and 6 intertwiners. Then we can rewrite the same thing in the following left picture. So in the left picture, we have 4 triple points and 2 crossings. Okay, we see that triple points are 1, 2, 3, 4 triple points, and also we have 2 crossings. So it means that we have 4 ordinary intertwiners and also 2 braiding intertwiners. And then this picture, the left picture, means that we have a composition of these 6 intertwiners. Then the left picture is the composition of these 6 intertwiners. But then look at this picture and suppose that these okay, we have some different level of thickness, but it doesn't matter so much. We can ignore this. So here we have this wire lambda, and this lambda continues as alpha lambda plus, and this alpha lambda plus continues as lambda, but basically we can identify this lambda and alpha lambda plus because alpha plus lambda is a certain extension of the original endomorphism, so somehow they are very similar, and in some sense essentially the same. Then here, so look at this picture and suppose that this is really a topological diagram. Then, so from lambda to alpha lambda plus and lambda, so this wire is, so this is an over crossing. So it means that this wire goes over other wire. So we can move this wire alpha plus lambda topologically to the right hand side. So we can move this one to the right hand side here. Then here we have a wire lambda to this. So we have a wire from this lambda to this lambda over mu, because this wire goes over mu. Then the new picture we get is this right-hand side picture. So the other labels are A1, A2, A3, A4. So now this alpha lambda plus disappears. So we just have a wire lambda and mu. So now here we have 6 wires. So we have A1, A2, A3, A4, and we have 2 more wires, lambda and mu. And then we have a crossing. So in the original picture of 6J symbols, we had 6 objects, but we had no crossing because we didn't use braiding. But here we have to use braiding. So something similar, something like a quantum 6J symbols, but here we now use braiding. So using braiding, we can make this new picture. So with crossing. So we have A1, A2, A3, A4, and also lambda mu with crossing of lambda and mu. So this is a new kind of 6J symbol, but with crossing. So this is our new picture for a kind of 6J symbol. And this is really a picture for alpha-induced connection. So the passage from the standard quantum 6J symbol to this new picture is really a passage from a ordinary connection to a new connection arising from the alpha induction. Then we can write down some explicit examples based on the ADE linking diagram. So suppose the original modular tensor category is something from the Wess-Zumino-Witten model, SU2 level K, or a quantum group, UQSL2, at root of unity. Then we have a fusion category, braided, actually a modular tensor category. In this case, the Frobenius algebras are well understood, are well classified. And then we have commutative Frobenius algebras corresponding to linking diagrams AN, D2N, E6, and E8. Okay, we have no commutative Frobenius algebras corresponding to 1 and also E7. We have no commutative Frobenius algebras corresponding to them. So only D even and E6, E8 appear here. And also, yeah, we have non-commutative one corresponding to D odd and E7. They are really non-commutative Frobenius algebras. Then, as I said, these Frobenius algebras correspond to extensions of conformal field theories. And the ones for D2N, they correspond to the simple current extensions. So they are kind of extensions of order, index 2, index 2 extension. They are rather easy. Basically just the cross product, a semi-direct product of order 2. And then the one for E6 and E8, they really correspond to conformal embedding at the SU2 level, which level 10, 10 and 28, yeah. So they really correspond to conformal embedding. Then the alpha induction for them is also well understood for many years. Then in the setting of connections, so a new kind of generalized quantum 6G symbols, connections arising from the alpha induction are exactly those on the ADE linking diagram, which I explained. So they also produce more connections generated by them, and this is the setting Okunian originally worked on. So this kind of alpha induction for connections were considered by Okuniano many years ago, but he considered only linking diagrams. So in today's talk, my construction is a vast generalization of his construction in the setting of braided fusion category. So then, as I said, we have a notion of flat connection. This is a particularly nice bi-unitary connection, which really corresponds to quantum 6J symbols in some sense. And then commutativity of Frobenius algebra and flatness of bi-unitary connections are really related. So if we have commutative Frobenius algebra at the beginning, then this construction, the picture below, this construction gives alpha-induced flat bi-unitary connection, so something particularly nice. And then this is because basically we have to compute the value of the following diagram. So here we have the same picture here, but the labels are different. So in this 4 parts, in the previous picture, we had some general labels A1, A2, A3, A4. But here we have all of these standard generator, iota. Iota is an original embedding from N to M, or the original embedding from one conformal field theory to a larger conformal field theory. And actually, in the case of E68, so this iota is something really corresponding to the conformal embedding. So in this setting, so this is a particular diagram, and then so we have to evaluate this picture, and it turns out that in this setting, because of some special choices of iota, in this setting, this diagram essentially has value 1 up to some trivial renormalization arising from Perron-Frobenius weights. So basically, this diagram has a value 1, and this value 1 comes from the commutativity of the Frobenius algebra. Basically, the commutativity of the Frobenius algebra corresponds to some elimination of braiding. So we can eliminate this central crossing in this way from the commutativity. Then we can eliminate this crossing, then we really get the standard picture for 6J symbols. Then we basically get value 1 in this situation. So in this way, we have value 1 and flat connection for the alpha-induced connection. So this is our standard picture, and this explains why we get a flat connection for E6 and E8 and for D even. But this is a proof for a completely general setting of braided fusion category. So this is our new construction. Okay, so today I stop here. Thank you very much.
Thank you very much for talk.
Okay, thank you. Ivan, you can continue. Sorry. Ivan. Not work. Thank you very much. Any comments, questions? Okay, no questions. It was some new topic for me, so I have not questions too. But very interesting, and I think it will be very useful to our participants. And maybe you can send to me not only the slides, but add some references on your papers in order we can continue to teach so interesting topic. Thank you again. Very nice, very interesting. And I repeat that it is the last seminar before the summertime. So thank you to the speaker. Very nice, very interesting. And bye-bye.
Yeah.